Hey students, welcome to Video2b. We're going to talk about geometric dimensioning and tolerancing and datums. So I am coming at this from the assumption that you remember some of what you were taught by either Dr. Alcuda or Dr. Yipoy in the past couple of years. And so it will be pretty important to base things off that. If you're having a hard time remembering that, then I would suggest that you spend some good quality time in chapter 13. Some of the reading is a little bit dry, but it's really important. We're going to be assigning GD&T callouts, and datums in this class are going to be incredibly important because we're talking about how you actually make things. And so datums are critical, as is GD&T, so that you can get the right, so that things fit together. All right, so remember with GD&T, we have some shape with some call out, like this hole on this part right here. But when it is just called out like this, we don't know much about the form of the hole. That hole could be at a little bit of an angle. It could be wandering as it's going down. There are all kinds of things. Now, the ASME standard says that the positions of that hole as they're called out would be true throughout the entire depth of the hole, but that doesn't mean that this hole is circular. We have 10,000ths on the position in each direction, and so that hole could be, you know, a serpentine back and forth as long as it stays within that that range. So it could look like that through the hole. That's of course a drastic amplification of what the errors could be with these small tolerances. But if we tried to fit a pin that were in an adjoining piece of material into this hole, it's unlikely that it would fit. So we need to add more information so that we can talk about not only the size of the hole, but also some of the form of the hole, and that form of the hole is going to imply or match the function. So how does this hole actually work with a pin or a bolt or whatever else whatever the reason for that hole is. So GD&T especially is important for how will the parts be assembled. So that's a lot of what we're going to. That's not by any means the only aspect. There are lots of other aspects. Some of the aspects deal with, is the part likely to fail in fatigue because of surface treatments and the way that you've done things to it. But primarily we're dealing, especially in this class, with the form and the function, and that's why we need GD&T. So just to remind you, we have this feature control frame. All feature control frames start out with the geometric characteristic. So in this case, this is true position. And then it has the tolerant zone and its shape. So the tolerant zone is 1.125, and it says that that is a diametral tolerant zone. So this would, to have a tolerance of 1.125, that must be millimeters, and this is a pretty big part to have that. But the diameter symbol right at the beginning of that says that this is a circular tolerance zone. If no tolerance zone is listed, it is assumed to be a square tolerance zone. So equal in X and Y, and lined up, X and Y lined up according to the datums that you've called out at the end. You can have modifiers like the maximum material condition here, the big M, and then after that is the list of the datums. And those datums are listed in order of priority. So A is the most important datum to this feature, then B, and then C. Okay. So a couple of things here. The datums can be called out at a maximum or least material condition. They can have a modifier as well. That doesn't make much sense on a surface, but it could if something were called out with a thickness, or if it's a hole or a shaft sort of feature, or a profile could be called out as a maximum material condition. So any of these, A, B, or C, could have that. All right. One thing that I want to talk about is that it is really important to make sure that you use the number of datums, or you identify the number of datums that are supposed to be used for a geometric callout. So to me, it is not totally clear that a true position callout should have 3 datums. Because when I look at this part over here, I have this block and I see that this edge over here is datum B and this edge over here is datum C. And I could easily think that the true position really is with reference to B and C, and that's going to call out the true position of this hole. But in fact, the most important data, the one that is listed first, is datum A. And what datum A does, that's this bottom down here. So this bottom surface sets a plane. It says parallel to this plane, parallel to the A plane, and this distance from B and this distance from C. If we haven't set up what that plane is, then what does it mean to be a certain distance from B? Is it along this flat? Is it along an edge? Is it vertical? Who knows? And so A is the most important datum. Okay, how do you make sure that you get the correct number of datum callouts when you are doing this? Well, there are 2 ways that you make sure. Because you're going to get it wrong, you're going to get points taken off if you don't have the correct number of datum planes. So 2 ways. The primary way to do that is to look at something like this form. And so this is in the back of your book. It is on page 404, and this form and then the tables that are after it will tell you how many callouts. It's not right on this part of it, but anyway, it will tell you how many callouts, how many datums have to be identified. And remember, some GD&T has 1, 2, 3 datums. There are some GD&T that have no datums. And so that's pretty important to remember also. So you need to get the number right. So the best way would be to look at a reference like this. Another way to do it would be to use a tool that helps you. For instance, the FTA workbench in CATIA will help you with that. Now, I have found the FTA workbench to not be 100% accurate, and it will let you delete or add datums that should not be there. So be really careful about that. No matter what you're doing in CATIA when you're putting these in, don't add or delete them. Make sure that you use the right numbers. So let's talk a little bit more about datums. What are datums? Well, a datum is a surface, a line, a plane, or a feature, and by line it can be an axis, and it is assumed to be perfect. And so you are taking some feature from this part, you're assuming it to be perfect, and then you're going to measure things from it. When we do datums and we assume them to be perfect, we also begin to assume things about their relationship to other datums. So if nothing is called out, then we assume that datums are along orthogonal axes, unless they are called out otherwise. And like I said, we assume them to be perfect and in the right location. How do we choose the datum features for a part? Well, it should have a functional relationship to the features that we're controlling. So if we have a cylinder or a hole, then what we're going to use is an axis, and that axis is determined by measuring a bunch of points in the bore or a bunch of points along the outside of the shaft, and then we do some averaging and a best fit line through the center of those points, and we create an axis. It's actually way more complex than you're expecting it to be. And one of the things that we're going to talk about in this class is, okay, you called that out as wanting to have GD&T with respect to this feature. What is that going to cost you in terms of measurement time? Because the way that you go and determine that that feature will, require 1 or 3 or 9 or 27 measurements, and each one of those costs you money because they take time. So the datum features, how will it mate to other parts in the assembly, is really important. So if two pieces are going to go together, then you might make one of those planes be a datum. If there's an edge that things fit together along, you might make that be the assembly. Holes, the axes of holes are often used. Datums need to be stable, so it needs to not be on something that's thin and wobbly. It needs to be in some part of the part that is going to stay where it is, both when you clamp it and when you let go. It needs to be accessible so you can get to it, and it needs to be repeatable as possible. So that, let's see, so how do you choose the primary datum? How do we go about this process? The primary datum is the main reference for all of the features. It is the most important for inspection and gauging. Often it is the biggest surface, or maybe it is the most important feature, and so you would use that. Sometimes a bore will be the most important feature for an entire part. If you think of some parts of an axle of a car, the assembly, bearing assembly that holds that, the hole that holds the bearings, that holds the axle, is by far the most important part. There can be other little lugs and things on there. They are completely secondary to that hole in the part. Often box-shaped parts, it is most important to use the biggest plane, so that it is very stable when you are using that plane to begin your inspection process. Secondary and tertiary datums have the same role as the primary, and they're used to measure the features that you can't measure from the primary. And so they may add some orthogonal axes to the part. They must be perpendicular to the primary datum and each other for the first 3 axes. Once you've gotten the first 3, then you can start adding datum features that are not perpendicular, and that will often happen. Okay. So what effects do they have? They have lots of effects. They have effects in the way that you measure things, the way that things go together, and they also have effects in the way that parts work together. So if we look at this part, what are the datums on this part? And it's pretty hard to tell, I would say. So you might say, well, it looks like these 2 edges are the datums up here, and that could be true, but not much is referenced to these 2 edges. I mean, this edge only has one thing referenced to it, which is the position of this hole. And if you dimension things this way, then the further out you go, the more that the tolerances cascade, and so they start to amplify as you move across the part, and so you get stack up on a part like this. This really doesn't tell you what the primary datums are. What I would say from this one is probably this hole, the right hole, is the primary datum, because from there you can get to both edges in the what looks like the Y direction here, and you can get to this right edge, and you can get to the other hole from here. And so this is probably the primary datum, or the primary datum might be the bottom surface, though we don't really know. And so this right hole is probably the most important. How would we grab this part with a robot? Well, it would be really hard to grab with a robot. What I would do is I would stick a pin in this hole that can expand, and then all of these other areas out here are going to be hard to grab. Why do I say that? Well, it's because we have tolerance stack up going out here, and so if the distance from hole to hole is wrong and the distance from the hole to the end is wrong, then those 2 can add together, and we can end up with a huge amount of variation that our robotic grabber has to be able to deal with. So the range of the gripper would have to be pretty huge. So how would we do this better? Well, if we label the part this way, it is clear that the left hole is now the primary datum. because you can see that both the hole and both ends of the part are referenced in X to this hole, and both the top and, or both of the 1 inch are referenced from the center line of these holes. Even though it's drawn to this hole over here, the assumption on this is that these two are along the same center line because it's not marked otherwise, and so that can be assumed. And so in this case, the gripper has to have, or does not have to have as big a range. And so this is a much more functional way to identify the part, and it's also probably going to function more like you actually wanted it to function. So there are some practicalities of datums. So sometimes the datum is implied and is not actually there. Sometimes it doesn't exist. So one example of that is that the axis of a cylinder, when you identify a cylinder as the datum, then the actual datum is the axis that is formed by that cylinder. And axes don't exist, right? It is a figment of our imagination and is an abstraction of that cylinder. It requires a lot of measurement and averaging, and then some method of somehow choosing what axis is most representative of that cylinder. And so sometimes axes don't, sometimes datums don't exist. You can't just measure the datum. You can't go find the datum. You have to do a lot of other measurements to calculate the datum. On some things, instead of a point being a datum, there will be a target or an area. And so this often happens on castings. And so because castings can vary quite a bit in size, and they may have rough surfaces, it doesn't make sense to have just a single point be the datum, because there might be a little hole, like a blowhole or something, right at that point. And so instead, they will call out a datum area or a datum target, and they may list a size of the contact that is supposed to hit that area. And what they're doing is having something that has a little bit of size to it so it can average out over that rough surface. And if there's a really sharp edge on that rough surface, when you press it onto that datum, it may squash down that sharp surface as well. And sometimes datum features get machined off. I think I wrote sometimes here, but I would say very, very often datum features get machined off. And so that means that you can measure a part. As you're going along, you can measure what a machine did, but later on it may be very hard to back out where something went wrong in a process if you only measure at the very end and you don't do some measurements down throughout the process, because often datums will get machined away, and then trying to backtrack to where was that datum before I machined it away for the next setup is really tough. One thing that you'll also find is sometimes datums don't exist on the part that you have. I used to make this connecting rod right here, and when we made this connecting rod, here is where the connecting rod goes. You can see this large bore down here goes around the crank of the engine, and this small, this is called the wrist pin, goes up inside the cylinder. And so our primary datum was the bore of this cylinder. And of course, we didn't have the bore of that cylinder. We didn't even have the cylinder. And we didn't have the wrist pin. All we had was the connecting rod. And so we had to make go from this abstraction of what the primary datum was to what our rod actually had, and then build out parts from there. But sometimes that meant that we had really tight tolerances on our part because there was stack up through the wrist pin, through the and through the cylinder and the piston. Okay. Maximum material condition, least material condition, and regardless of feature size. We're going to cover these pretty quickly. If you don't remember the concepts, you need to go back and read them and read about the virtual condition. You need to make sure that you understand this well. However, that being said, I will say in this class and in most of life, the maximum material condition is typically the most useful to use. Why is that? Well, if I have regardless of feature size, we'll look at it in a minute, but it means no matter what size, if I have two pins that need to fit in a hole, so a stepped pin and it needs to fit in a hole, because of the bonus tolerance, the maximum material condition is really the best way to put two things together. And that is because as a pin gets smaller, it has more ability to move around and it will still fit in the hole. And so that's the way that life works well. So when would you not want to use that? Well, sometimes you need something to be the right size to make sure that it's strong enough. And if you're in that case, then you would use regardless of feature size. LMC is not super useful. Why not use regardless of feature size all the time? Well, for one thing, it's much more expensive because you have to make every part exactly right. You can't undersize it and have it work and fit together well. You have to make every part exactly right, and so it becomes much more expensive to do. So, excuse me. So remember, the maximum material condition is when there is the maximum amount of material there. For a shaft, that is the largest diameter shaft, and for holes, it is the smallest diameter hole. As you move away from the maximum material condition, remember, you will then gain the bonus tolerance. Least material condition is the opposite. The shaft has the largest diameter, the smallest diameter, and the hole has the largest diameter. And then regardless of feature size, the feature size has no effect on the form tolerance. Remember that regardless of feature size is the default. And so if you don't set something else, it's going to be regardless of feature size, which often means that at least the cost of making your part will be considerably higher, and you'll have many more failures where things will not fit together. So maximum material condition, many more of your parts that you make will fit together. That being said, MMC is harder to measure often. Actually, that's not totally true. It depends on the kind of gauge you're using, but it can be harder. Remember, we have this virtual condition boundary, and that is the worst case boundary, and then it is the way that we can check to make sure if two things will go together. So for a hole, the virtual condition boundary is the maximum material condition minus the geometric tolerance. For a shaft, it is MMC plus the geometric tolerance. Okay, let's look at an example of that real quick. So if we have a shaft called out, and the shaft can be between 1 and 1.020 inches, so it has a 20 thousandths or tolerance on it, and then we have a true position of a diametral true position of 5 thousandths of an inch with a maximum material condition. Okay, so what does this mean? This means that when we look at this part, we have the 1 to 1.020. Remember, we're going to choose the maximum material condition for a shaft is the biggest shaft. That's when it has the most material. So that's 1.020. And then we add on this true position because that will make the tolerance a little bit bigger. And so that makes our virtual condition be 1.025. And so then if we have, if we're looking at, okay, what shaft fits into that category, the shaft can have a bend in it. The diameter measured at any point has to meet the diameter tolerance, but because we have this larger zone from adding the maximum material condition and the true position tolerance, it allows us to not have a perfectly straight shaft. It will still fit into the location where we want to use it. Okay. Two rules. These, I don't know how helpful the rules are, but where only a tolerance size is specified, the limits of size of an individual feature prescribe the extent to which variations in its geometric form as well as size are allowed, given that no element of the actual feature shall extend beyond the boundary of the perfect form, at MMC, and the actual local size of the feature may at any cross-section shall be within the specified tolerance. All right, what does that mean? Well, what that means is if we are given a hole and it has 750 plus 5 minus 0, if we have something that is triangular shaped, as long as it doesn't go outside that range from 750 plus 5 is 755 or 750 minus, as long as it doesn't go outside that range at any cross section, and including the form, so if it has some angle to it, if it doesn't go outside that condition, then it fits. This says that the tolerance of size goes all the way through the hole, and so we have to assume that it can be, that it just goes all the way through the material, even though it's only specified on one end of the material. Rule number 2 is that RFS applies if you don't call out MMC or LMC. And so that's really important to remember. So remembering again, if we have this little pin, so we have a stepped pin where there's an outer diameter here, and I'm sorry, not an outer, an outer diameter that's large and a smaller outer diameter. The outer diameter is the datum. You can see that it is specified as datum D, and being at 3 inches, this ought to have a tolerance on it, so maybe that's picked up by the blanket tolerance. And then we look at the smaller feature here, and the smaller feature has both a size tolerance and it has a true position tolerance, that is with respect to D. And so we have 2 different ways that can be done. One is A, where it is a true position with respect to D, and B is a maximum material condition of 5 thousandths. So which of those will help us out more? Well, generally, if this is going into a hole where the concentricity of these 2 matters, and so maybe it's a stepped hole where it's going to need to fit both the large diameter and the small diameter, the maximum material condition works a little bit better, because it doesn't matter what size, well, it does matter within the size range that's here. If the small diameter of this part is undersized, then it does not have to be positioned as precisely, and it will still fit in the hole as reference to datum D. And so that's really helpful a lot of the times. It's also truly useful most of the time. It is the way that things go together best. So we can get some bonus tolerance here. So if our smaller shaft is its full diameter, then all we get is the position tolerance, and our total position tolerance is 5/10, just like it said. So this is looking at option B. But if our shaft diameter is 5 thousandths undersize, then we get to add in, we get to take this 5 thousandths, which is the difference between our actual size and the maximum material condition, and add it to our position tolerance, and now our position tolerance is 10 thousandths. What does that mean? Well, it means that our shaft, because it is smaller, could move further to the side and the parts would still fit together. So that is really helpful. Okay, so that's a whole lot of a really quick review of this. If you are having a hard time remembering this, I need you to go and review Chapter 13. In this class, we're going to be assigning geometric dimensioning and tolerancing to make things fit together, to understand them. And so you need to be ready to be able to do that based on what you learned in Dr. Alcuda and Dr. Yapoi's classes. And so if you need a refresher, please go look at those chapters before class. And then in class, we're going to be doing some application of these. And then as we move through and you're doing your projects, I'm going to expect on your projects that you're going to put good GD&T and an appropriate amount. And an appropriate amount means you put it where you need things to fit together, And where it isn't critical, you don't put GD&T, because the cost of measuring GD&T is pretty significant. So it's important to make things fit together, but you don't just add it on just because to try to look cool or whatever, to show your engineering chops. All right, see you in class.